you feel time passing. Right now, every second, every breath. But the deepest equations in physics don't. One of Einstein's own students proved that time travel into the past is mathematically legal. Then, decades later, physicists wrote the master equation of the whole universe, and accidentally left time out of it entirely. We're going to go inside a rotating universe where you can loop back to yesterday. We'll find an equation with no clock, and then we'll hit a 2025 discovery so strange that reality itself might need to be rebuilt from scratch. If you enjoy the journey, like and subscribe. It keeps us going. Now, let's find out if time is even real. Close your eyes for 1 second. You just felt time pass. That sensation is so constant, so automatic, that you've never once questioned it. Time moves forward. The past is behind you, the future is ahead. It feels as obvious as gravity pulling you into your chair. But here's the thing. Physics, the science that explains how everything in the universe actually works, has never been able to confirm that feeling is real. And the deeper scientists look, the stranger it gets. Start with something simple. You remember this morning? You don't remember tomorrow. That gap between past and future feels enormous. It feels like the defining fact of existence. But when physicists write equations to describe the universe, those equations almost never care which direction time runs. You can play most of them backward, like a video in reverse, and they work just as well. The math doesn't prefer a direction, the math doesn't move at all. So where does the feeling come from? Part of the answer involves something called entropy. It's just the amount of disorder in a system. Your bedroom gets messier on its own. It doesn't spontaneously tidy itself. That one-way drift from order to disorder is one of the only things in physics that actually picks a direction. Scientists think that arrow of disorder might be the reason you experience time as moving forward rather than backward. But that's already strange. It means the direction of time you feel in your bones might come from the behavior of scattered molecules rather than from something fundamental about the universe itself. And it gets stranger. Think about a film crew recording your life. Every frame they capture is a frozen snapshot. Stack a million snapshots in order, and you get the illusion of movement. Some physicists believe the universe works exactly like that. Every moment in time already exists, locked in place like a frame in a reel. What you call now isn't a special moving edge sweeping across reality. It might just be the frame you're currently inside, with no more special status than any other. That idea has a name. Physicists call it the block universe. Past, present, and future, all sitting there together in one fixed structure, the way pages in a book all exist at once, even while a reader moves through them one at a time. If that's true, then the feeling of time flowing is something your brain generates. The sensation of moving forward, of becoming, of getting older, would be a story your mind tells itself, not a direct readout of reality. That's an uncomfortable thought. But even that isn't the most unsettling part. The most unsettling part is what happens when you try to write one single equation that describes the whole universe at once. Scientists have done exactly that, and what they found hiding inside that equation stopped the entire field cold. There was no time in it. The universe's master equation, the deepest mathematical description of everything that exists, was written without a clock. Scientists didn't remove it on purpose, it just wasn't there. And when the smartest physicists in the world sat down to figure out why, they found themselves staring at a problem that has never been solved. Your sense of time is so vivid, it feels unquestionable. But the universe, at its most fundamental level, might not share that experience at all. And the story of how physicists discovered that starts with one man, one birthday gift, and one equation that bent time into a loop. Before Einstein, time was simple. Isaac Newton described it in the 1600s, and barely anyone questioned it for 200 years. Time was a river, flowing at the same speed everywhere, for everyone, always. It didn't matter if you were standing still or flying through space. The clock ticked the same. The universe shared one heartbeat. That picture felt so obviously correct that scientists treated it as a background fact of reality. Time was the stage, everything else played on it. Einstein walked onto that stage in 1905 and quietly removed the floor. He was 26 years old, working as a patent clerk in Switzerland, and he published a paper that changed every assumption physics had ever made about time. His theory of special relativity started from two simple rules. First, the laws of physics are the same for anyone moving at a constant speed. Second, light always travels at the same speed, no matter how fast the person measuring it is moving. Those two rules sound harmless. They aren't. If light's speed never changes, then time has to. Two people moving at different speeds will disagree about how long something takes. They'll disagree about whether two events happened at the same moment, and both of them will be right. There's no third observer floating above the universe who can settle the argument by checking the master clock. That master clock doesn't exist. Picture two friends standing on a train platform. One stays still, one gets on a train moving at almost the speed of light. They each carry identical clocks. When the train comes back, the clocks show different times. The traveler aged less. The events they each experienced didn't happen in the same order from their different perspectives. This isn't a malfunction. This is exactly how the universe behaves. Scientists have tested this with atomic clocks on airplanes. The clocks tick slightly differently depending on altitude and speed. The effect is tiny at everyday speeds, but it's real, it's measured, and it matches Einstein's predictions perfectly. Now here's what that means for time itself. If two people can experience different amounts of time between the same two events, then there is no single cosmic now that applies to everyone. The present is not universal. It's local, your now is yours. Someone moving past you at a different speed has a different now. Both are equally valid. Newton's river became a landscape of streams, each running at its own pace, none of them more correct than the others. 10 years after his first paper, Einstein pushed even further. His theory of general relativity showed that gravity also warps time. Massive objects like planets and stars actually slow down the clocks near them. A clock at sea level ticks slightly slower than a clock on a mountaintop because it's sitting deeper inside Earth's gravitational field. The GPS satellites circling the planet have to correct for this effect constantly, or the maps on your phone would drift by miles every day. So time bends, time stretches, time runs faster in some places and slower in others. The universal stage Newton described doesn't exist. Time is not the background. Time is part of the structure, and that structure changes depending on where you are and how fast you're moving. Einstein himself found this deeply unsettling. He spent years trying to find the deeper principle that might restore some kind of order beneath the chaos. Instead, in 1949, an old friend handed him a birthday gift, and it made everything worse. Einstein didn't just change how time works, he changed what time is. Before his work, space and time were two separate things. Space was the three-dimensional room everything lived in. Time was the invisible ruler measuring when things happened. They were partners, but they were different. Einstein merged them into one thing: space-time. Think of it like this. Every event in the universe happens at a location in space and at a moment in time. Combined, that gives you 4 pieces of information: left, right, forward, backward, up, down, and when. Those 4 dimensions woven together form space-time. And space-time is not just a useful bookkeeping system. It's a physical thing. It has shape, it can flex, mass bends it. Picture laying a heavy bowling ball on a stretched rubber sheet. The sheet curves inward beneath the ball. Now roll a marble nearby. Instead of traveling in a straight line, the marble curves toward the bowling ball, following the shape of the sheet. That's how gravity actually works. Earth isn't pulling the moon with some invisible force reaching across empty space. Earth bends space-time, and the moon follows the curve. But space-time isn't just bent in the space dimensions, it's bent in the time dimension too. And that's where things get genuinely strange. Near a very massive object, time slows down. A clock sitting on the surface of a neutron star, one of the densest objects in the universe, would tick so slowly that a year on that surface might equal thousands of years out in open space. The geometry of space-time near extreme mass is so distorted that time itself compresses. The closer you get to the center of a black hole, the more extreme this becomes. At the event horizon, the boundary you can't come back from, space-time geometry curves so sharply that the direction of time and the direction pointing toward the center become the same thing. Falling inward stops being a choice. It becomes as unavoidable as the future. That detail is worth sitting with. Inside a black hole's event horizon, moving toward the center is as mandatory as moving forward in time. Time and space have literally switched roles. Now think about what space-time geometry means for the universe as a whole. If space-time is a physical structure that can be shaped, curved, and stretched, then the universe is made of this stuff. The Big Bang wasn't an explosion inside an existing space. It was the beginning of space-time itself. Space was created in that event. Time was created in that event. Before the Big Bang, the concept of before may not have applied. That means asking what happened before the Big Bang is like asking what is south of the South Pole. The question assumes a structure that doesn't exist in that direction. This is where geometry becomes philosophy whether scientists want it to or not. If time is a dimension of space-time, and space-time is a physical structure that had a beginning, then time is not eternal. It had a starting edge. And if it had a starting edge, maybe it also has internal structure, twists, folds, and regions where the geometry behaves in ways human intuition was never built to handle. That's exactly what Kurt Gödel found. He didn't use a telescope or a particle accelerator, he used a pencil. And the shape he drew on paper bent time into a loop. In 1949, the world's most famous physicist turned 70 years old. His colleagues at Princeton wanted to honor him properly. They put together a collection of essays from brilliant scientists and thinkers, each one offering Einstein a gift of ideas. Kurt Gödel, the legendary logician and mathematician, decided his gift would be a new exact solution to Einstein's own equations. He handed Einstein a universe that ran backward. Gödel had discovered that Einstein's field equations, the mathematical heart of general relativity, allowed for a type of universe that rotated slowly, steadily, the whole cosmos spinning around some central axis. Nothing in Einstein's equations actually forbade this. Gödel simply asked, what happens if I plug in a universe that spins? The answer came out clean, mathematically precise, and deeply unsettling. In a rotating universe, space-time doesn't just bend near massive objects, it twists globally. The rotation of the entire cosmos drags space-time around with it the way a spinning spoon drags honey. And in that twisted geometry, something extraordinary becomes possible. Paths through space-time can curve so much that they loop back on themselves. Physicists call these closed time-like curves. Strip away the jargon and the meaning is stark. A traveler following one of these paths through space would eventually arrive back at their own past. The same coffee shop, the same Tuesday afternoon, the same version of themselves sitting at the table one loop earlier, and critically, that traveler never breaks any rule. They never exceed the speed of light, they never violate Einstein's laws locally. The universe simply has a shape that allows the journey. This is where the birthday gift stopped being academic. Gödel's point was never really about time travel as a technology. His deeper argument was philosophical, and it targeted Einstein directly. If your theory of space and time, your most complete description of the physical universe, allows for futures that loop back into the past, then that theory is missing something. Ordinary cause and effect requires that causes come before their effects. In Gödel's universe, a traveler could arrive before they departed. Effect before cause, the whole framework of why anything happens because of anything else, begins to collapse. Einstein read the solution carefully. He was troubled by it. He wrote that the possibility Gödel had uncovered was disturbing, and he tried to argue that physical and practical obstacles would prevent anyone from actually completing such a journey. But he couldn't argue that the mathematics was wrong. He couldn't point to a law in his own theory that prevented the loop from existing. The equations permitted it. That gap between what the equations allow and what reality seems to enforce became one of the defining puzzles of modern physics. Gödel believed this gap proved that general relativity was not the final word on time, that beneath Einstein's beautiful geometry, some deeper principle must exist that forbids the loops. A rule not yet found, a constraint the equations were missing. Decades later, physicists still haven't found that rule. And here's the thing that makes Gödel's universe even harder to dismiss. The loops aren't a flaw in the math. They're a clean, exact, elegant prediction. The universe he described doesn't contradict relativity. It uses relativity at full strength, perfectly, to arrive at something that should be impossible. Which raises the obvious question, how exactly does a spinning universe produce a time loop? Picture the universe as a massive storm. At the scale of a planet, a hurricane has winds that circle around a central eye. The spinning of Earth itself drives that rotation. Now scale that image up by a factor so enormous it makes the Milky Way look like a grain of sand. In Gödel's universe, the entire cosmos rotates the same way. Everything, every galaxy, every star, every particle circles slowly around a central axis. That image alone is strange, but the real weirdness isn't the spinning. It's what the spinning does to space-time. Einstein showed that mass warps space-time. Gödel showed that rotation warps it in a different way. When a massive body spins, it doesn't just pull nearby objects toward it. It drags space-time itself in the direction of its rotation. Physicists call this frame dragging. It's a real effect. Scientists have measured it around Earth using satellites. Earth's rotation subtly twists the space-time near it, like a stirring rod twisting water in a glass. In Gödel's universe, that effect doesn't just happen near one spinning object. It happens everywhere, uniformly, because everything is rotating together. The entire fabric of space-time is being twisted in one consistent direction across the whole cosmos. Now think about what that means for a traveler. In normal space-time, if you draw a line representing your path through space and time, that line always moves forward through the time dimension. You can travel in any direction through the three space dimensions, but you are always carried forward in time. That forward direction is locked in. It's part of the geometry. In Gödel's rotating space-time, the geometry itself tilts. The twist introduced by cosmic rotation gradually tips the forward time direction sideways. Far enough from your starting point, the direction that space-time says is forward in time has curved around so much that it now points back toward your past. A traveler moving through this space at a long enough distance from their starting point would be moving forward in time by every local measurement they could make. Their own clock would tick normally. They wouldn't feel anything strange. They would simply be traveling. But the geometry they're traveling through would curve their path through space-time into a closed loop. When they arrived at the end of that loop, they would be sitting in their own past. No force, no machine, no magic, just the geometry of a rotating universe, carrying them there the same way Earth's gravity carries a ball in a curved arc, even though nothing is pushing it sideways. The closest everyday comparison is an airplane following a straight path above a curved Earth. The pilot points the nose forward and flies in what feels like a perfectly straight line. But the curvature of the planet means that straight line eventually curves around and brings the plane back to where it started. In Gödel's universe, space-time's curvature does something similar to paths through time. Scientists confirmed that our universe does not appear to rotate at this global scale. Modern observations don't show the large-scale swirl Gödel's model requires. So, we almost certainly don't live in his specific cosmos. But here's the part that never stopped mattering. Gödel found those loops using nothing but Einstein's equations. He didn't invent new physics. He used existing physics with full mathematical precision. That means the laws governing our universe can produce time loops. The rules that describe our reality don't automatically prevent them. And if the equations allow it here, the problem isn't the geometry of one hypothetical universe. The problem runs deeper, much deeper. There's a rule in Einstein's physics that almost everyone knows. Nothing travels faster than light. Light covers about 186,000 miles every second. That number is a hard ceiling. No signal, no object, no piece of information can beat it. And this limit is part of why causality holds together. If causes always travel toward their effects at speeds at or below light, then causes always arrive before effects. The sequence is protected, the arrow points one way. Gödel's time loops seem like they should violate this. If you arrived before you left, something must have moved faster than light, right? Wrong. This is the part that unsettles physicists most. A traveler completing a closed loop in Gödel's universe never once exceeds the speed of light. At every single point along the journey, their local measurements are perfectly normal. Their clock ticks, their instruments read expected values, they accelerate and decelerate using ordinary force. Nothing about their local experience suggests anything unusual. The loop doesn't come from traveling fast. It comes from the shape of space-time itself. Think of walking in a perfectly straight line on the surface of a globe. Every step you take is locally straight. You never turn, but the curvature of the sphere means your perfectly straight path eventually brings you back to your starting point. You didn't violate any rule of walking. The geometry did the work. Gödel's rotating universe does the same thing to paths through space-time. The traveler follows the correct local rules at every moment. Space-time's global curvature handles the rest. And that is exactly why causality breaks. Causality doesn't fail because something moved too fast. It fails because the geometry of the universe connects future moments back to past moments. Once that connection exists, the chain of cause and effect can run in a circle. A traveler could leave a note for their past self. They could prevent their own departure. They could hand something to someone who hasn't been born yet. The most famous version of this problem has a name: the grandfather paradox. You travel back and prevent your own grandfather from having children, but then you were never born. So you never traveled back, so your grandfather had children after all. So you were born, so you traveled back. The loop has no stable resolution. Cause eats its own tail. Einstein's equations don't solve this problem, they produce it. Some physicists have proposed a possible escape. Stephen Hawking suggested a principle he called the chronology protection conjecture. The basic idea was that the laws of physics, perhaps through quantum effects not yet fully understood, conspire to prevent time loops from actually forming. Every time a situation arises that could create a closed loop, some physical process shuts it down before it completes. It's a reasonable hope. It has never been proven. It remains a conjecture, not a law. Physicists suspect it might be true. They cannot confirm it. And the equations that would need to enforce it, including the very quantum gravity equations that might settle the question, remain unfinished. So Gödel's universe sits there in the record books, mathematically clean, physically consistent, an exact solution to the equations that govern our reality. And inside it, cause and effect are optional. Physicists don't lose sleep over Gödel's specific rotating universe. They lose sleep over what it reveals about the equations themselves. Those equations are powerful enough to describe the Big Bang, black holes, and the expansion of space. But they don't come with a built-in guarantee that tomorrow can't reach backward and strangle yesterday. That's the warning label Gödel attached to relativity with a birthday gift. And understanding it makes the next discovery hit even harder. Let's be clear about something. Our universe, the one you wake up in every morning, almost certainly does not rotate the way Gödel's model requires. Modern telescopes have mapped hundreds of millions of galaxies. Researchers have looked for signs of large-scale cosmic rotation in the way those galaxies are distributed, in the ancient light left over from the Big Bang, in the structure of galaxy clusters stretching across billions of light years. The measurements are consistent and firm. Our universe shows no evidence of the global spin Gödel's solution demands. We are not in his universe. That much seems settled. But the lesson from Gödel's work was never about his specific universe, it was about the equations. Einstein's field equations are the rules that govern how matter and energy shape space-time. They are not just a description of our universe, they are a mathematical framework that describes all possible universes consistent with the laws of general relativity. Gödel's rotating cosmos is one entry in that enormous catalogue of possible worlds. The problem is that the catalogue contains entries that break time. When a set of physical laws allows solutions where causality collapses, That's a significant warning about those laws. It means the laws don't intrinsically protect the thing we most depend on for reality to make sense, because before effect isn't built into Einstein's equations as a guarantee. It seems to be a feature of the specific initial conditions of our universe rather than a universal principle. Think of it like building codes for a bridge. A bridge can be perfectly engineered and still contain a design flaw that would cause it to collapse under one specific combination of load and wind, even if that combination never actually occurs. The fact that the bridge is still standing doesn't make the design flaw disappear. The flaw is real. It matters. It tells you something important about the limits of the engineering. Gödel's universe is that design flaw in Einstein's theory, and physicists have spent decades probing what it reveals. Some have tried to add new constraints to the equations to rule out closed time loops, but every attempt to simply forbid them by hand has looked arbitrary. The equations don't offer a natural stopping point. Any rule added to block the loops seems like a patch rather than a principle. Others have argued that the real answer must come from quantum mechanics. Perhaps the behavior of matter at the smallest scales introduces effects that prevent time loops before they can form. That argument is plausible, but it requires a unified theory of quantum gravity, a complete description of both the very small and the very large that physicists have spent the better part of a century trying to write and haven't finished yet. Gödel himself believed the problem went even deeper. He thought the time loops were telling you that time, in the way humans intuitively understand it, is not fundamental to the universe. He believed the passage of time was something like an appearance, a pattern generated by the structure of reality rather than a bedrock feature of it. That idea was considered philosophical speculation in 1949. By the 1960s, it had transformed into an actual equation, and that equation erased time more completely than Gödel ever did. In the 1960s, two physicists sat down to do something no one had ever successfully done. They tried to write a single equation for the entire universe. John Wheeler and Bryce DeWitt were working in a field called quantum cosmology. The goal was to apply quantum mechanics, the framework that governs atoms, electrons, and the behavior of the very small, to the universe as a whole. A complete theory of everything would need both quantum mechanics and gravity to work together. The Wheeler-DeWitt equation was the first serious attempt to build that bridge. They started with the best tools available. They took the core mathematical structure of quantum mechanics and tried to extend it to describe the whole cosmos. In ordinary quantum mechanics, you describe a system with a wave function, a mathematical object that encodes every possible state the system could be in, and you track how that wave function changes over time. So they wrote the wave function of the universe. And when they tried to write down how it evolves, they ran into something unexpected. The equation they produced had no time variable in it. In normal quantum mechanics, the equation that governs how a system changes is written with time explicitly included. There's a term that represents the clock. The wave function of an atom evolves because time passes, and the equation tracks that evolution second by second. In the Wheeler-DeWitt equation, that term vanished. The wave function of the universe doesn't evolve with respect to time in the equation. It just sits there, static, frozen. A complete, unchanging mathematical object that describes every possible configuration of the universe all at once, with no arrow pointing from past to future, no moment labeled now, no clock measuring anything. Physicists called this the problem of time, and it wasn't a small technical glitch to be patched. It was a structural feature of the equation itself. Time disappeared because when you try to write quantum mechanics for the universe as a total system, there is nothing outside the universe to serve as a clock. In ordinary physics, you measure time by comparing one process to another. You count the oscillations of an atom. You track the swing of a pendulum, but those comparisons always involve a reference outside the thing being measured. The universe has no outside. There is no cosmic stopwatch floating beyond the edge of everything, ticking away while space-time evolves. When the universe is the system, the question of what the system is evolving with respect to has no answer. The math reflects this honestly and without apology. Time drops out. The implications pile up fast. If the universe's most fundamental description has no time variable, then time is not a basic ingredient of reality. It's something else. Something that appears at some level but isn't written into the deepest laws. Something like temperature or color or texture, things that exist at the level of experience and everyday physics but dissolve into something more basic when examined closely enough. The universe's master equation looks at everything and sees a single frozen state. No before, no after, no change. Just a wave function. And the question that has driven physicists half crazy ever since is simple. If the universe is fundamentally timeless, why does every single moment of your life feel like it's moving? Take a photograph of a bonfire. The image shows bright orange flame, dark smoke, glowing red embers. You know it's hot, you know the wood is burning, but the photo itself doesn't move. It captures one moment and holds it perfectly still. The fire in the photo doesn't spread, the smoke doesn't rise, the embers don't cool. The Wheeler-DeWitt equation describes the universe something like that photograph. All the information about everything that could exist is encoded inside it. Every galaxy, every atom, every possible arrangement of matter and energy. But the equation itself doesn't run. There's no mechanism inside it that says this state becomes that state after a certain interval. It describes the universe as a complete static mathematical object, the way the photograph captures the fire without actually being on fire. This is a hard concept to absorb because human experience is built entirely on change. You eat breakfast, then you go to school, then you come home. These events happen in order. You experience them as a sequence. The idea that the universe at its most fundamental level might not be ordered in sequences feels like being told that the flaw doesn't exist. But here's the specific technical problem that makes this more than philosophy. In quantum mechanics, every physical system has a wave function. That wave function evolves according to an equation called the Schrödinger equation. The evolution is smooth, continuous, and time-dependent. You can ask, what is the wave function of this electron right now? What was it 1 second ago? What will it be tomorrow? The equation gives you answers because time is inside it, driving the evolution forward. When Wheeler and DeWitt applied this logic to the entire universe, time disappeared from the equation for a precise reason. In general relativity, time is not a separate background. It's part of the geometry of space-time, which is itself part of the system being described. When you try to quantize gravity, time gets absorbed into the thing you're calculating, rather than remaining the parameter you're calculating against. The result is an equation where the universe's wave function doesn't evolve. There's no parameter for it to evolve with respect to. The equation is a constraint. It says, these are all the valid configurations of the universe. Here they all are. And then it stops. What this means for physics is quietly radical. Every process you know, the formation of stars, the expansion of space, the birth and death of galaxies, happens because of change over time. If the deepest description has no time, then all of that becomes something that must emerge from the static structure, like music somehow emerging from a silent score. The change you experience is real at the level you experience it, but it may not be real at the level of the fundamental laws. The analogy that helps most is a movie stored on a hard drive. On the drive, every frame exists simultaneously. The ending is there, the beginning is there, every scene in between is there, nothing moves, nothing evolves. But play it through a projector, and time appears, characters develop, stories unfold. The drive is the Wheeler-DeWitt equation. The projector, the thing that makes sequence and duration appear, is something physics still hasn't fully identified. What it might be is something far stranger than a projector. It might be you. A frozen universe sounds like a dead universe. If the master equation has no time inside it, if the wave function of everything just sits there like a statue, then how does anything move? How does the sun rise? How do you age? How does anything happen at all? This is the question that physicists have spent decades trying to answer, and the leading responses are more creative than you might expect. The first major idea is called the Page-Wouters mechanism, developed in the early 1980s. Don Page and William Wouters proposed something elegant. Time doesn't need to be in the equation. You just need two parts of the universe to be correlated with each other. Here's the idea in simple terms. Imagine a clock and a camera in the same room. The clock's hands are at 3 o'clock. The camera shows a person sitting in a chair. Now imagine another version. Clock at 4 o'clock, person standing by the window. Then another, clock at 5, person walking out the door. Each of those is a separate, frozen snapshot. No snapshot moves on its own. But if you're the person in the room and you look at the clock, you can tell where you are in the sequence. The clock's reading correlates with your position. Change becomes readable, even in a static structure, because different parts of the system carry information about each other. Page and Wouters argued that this is exactly how time emerges in the universe. Parts of the universe act as clocks for other parts. You experience duration because your brain, your memories, and the physical processes around you are correlated with each other in the same way. The frozen wave function contains all of those correlations baked in. When you look at any part of it from the inside, you see change, because change is the pattern of how things correlate. Time isn't the container holding the universe. Time is a relationship between parts of the universe. The second idea goes even deeper. It comes from thinking about what an observer actually is. When you experience time passing, something physical is happening inside you. Your neurons fire in patterns. Your memories record states. Your body processes food and ages. All of this is physical change, and physical change, even in a timeless universe, can exist as a correlation within the wave function. An observer isn't outside the equation looking in. An observer is part of the equation. The experience of time comes from being a physical system that encodes its own history. A rock doesn't experience time. It has no memory, no internal change that records sequence. A bacterium has a tiny bit more. A human brain has an enormous amount. The richer the internal structure, the more vivid the sense of time flowing. On this picture, time is real. Your experience of it is real. But what it is, fundamentally, is the pattern of correlations inside a frozen mathematical object. This sounds abstract. The results are concrete. A 2025 analysis from Cambridge found that even without any external time parameter, the Wheeler-DeWitt framework can produce all three features you associate with time. Ordered succession, so events have a clear before and after. Measurable duration, so intervals feel like they have actual lengths. And directionality, so past and future feel different. Those features emerge from the structure of correlations inside the wave function. Time doesn't flow. Time is a shape. And yet, even that discovery wasn't the strangest thing waiting for physicists who kept pulling the thread. Stand in a forest. You want to know what time it is. You have no watch, no phone, no clock of any kind. But you look at the sun, its position in the sky tells you roughly where you are in the day. You look at the shadows of the trees. You estimate the season from the temperature. You figure out it's probably mid-afternoon in late autumn. You just used the environment itself as a clock. You didn't need an external, separate timekeeping device. You used one part of the natural world to measure another, the sun's position relative to the horizon, the shadow's length relative to the tree, relationships between things told you where you stood in time. This is the heart of a major response to the Wheeler-DeWitt problem, relational time. The idea has roots in the work of philosophers and physicists going back centuries, but it became a serious scientific program in the late 20th century. The core proposal is simple. Time is a relationship. It is what you get when you use one physical process inside the universe to stand in for a clock and measure the evolution of everything else relative to that process. In practice, physicists call this choosing an internal clock variable. Here's how it works mathematically. The Wheeler-DeWitt equation has no time parameter, but it does contain many physical variables describing the shape of space, the distribution of matter, and the behavior of fields. Some of those variables behave in predictable monotonically changing ways. They only go in one direction. They never repeat. A variable like that can be relabeled as a clock. Once you do that, you can ask, how does everything else in the universe look when this particular variable has a certain value? How does it look when the variable has a different value? The answers give you something that works exactly like a time-ordered sequence of states. The universe evolves relative to the internal clock, even though the master equation has no external time at all. Think of it like reading a novel. The pages don't have absolute timestamps attached. But the plot evolves because each page carries information that only makes sense in the context of the pages before it. The clock is the progression of the story. The characters experience change relative to each other and to the plot's development, not relative to some external universal calendar. The elegant feature of relational time is that it matches how time actually works in observable physics. You never directly measure time itself. You measure change, you count the oscillations of a cesium atom to define a second, you count the repetitions of Earth's orbit to define a year. Every measurement of time is secretly a measurement of change in one physical system used as a reference for another. The deep laws may have simply been reflecting this reality all along. There is no master clock because no master clock was ever needed. The universe keeps its own time internally through the web of correlations and changes that physical systems impose on each other. But this solution comes with a discomforting caveat that physicists discovered almost immediately. Different choices of internal clock produce different quantum theories. If you pick one variable as your relational clock and do the quantum calculations, you get one set of predictions. If you pick a different variable, you get a different set. The quantum time that emerges depends on which part of the universe you decided to use as your stopwatch. Two physicists building two different relational quantum theories of the same universe might end up with theories that disagree about what happens at extreme scales. That inconsistency hasn't been resolved, and it hints at something deeper about what time actually is. Not a single clean feature of the universe, but a perspective, an angle from which you're looking at a structure that doesn't require time at all. Hold your hand near a campfire. You feel heat. Real, vivid, undeniable heat. Now describe one single atom of smoke above that fire. Is that atom hot? The question doesn't make sense. Atoms don't have temperature. Temperature isn't a property of individual atoms. It's a property of enormous collections of atoms moving with varying speeds. Temperature is what happens when you have billions of particles bouncing off each other in a disordered way. It emerges from the collective behavior of a system. It doesn't exist at the level of a single piece. Heat is real. You feel it. It affects your body. It drives weather, cooking, and chemistry. But zoom in far enough and it vanishes, replaced by individual particles with individual speeds, none of which is hot or cold by itself. Physicists call this an emergent property, something real and measurable at one scale that has no direct counterpart at a deeper level. The argument for emergent time uses the same logic. Time might be real. The sequence of events you experience might be genuine. Your memories, your aging, the growth of a plant, all of it might be accurate and real. And yet, time might have no existence at the deepest level of physics, exactly the way temperature has no existence at the level of a single atom. This idea shows up repeatedly in serious physics, and it has several different forms. The simplest version focuses on entropy. Entropy is a measure of disorder. A shuffled deck of cards has high entropy. A perfectly sorted deck has low entropy. The second law of thermodynamics says entropy in a closed system almost always increases. Disorder grows. Order falls apart. This one-directional trend is what gives time its arrow. You remember the past because the universe was more ordered then. Footprints in sand mean someone walked there before, not after. Broken cups don't reassemble. Fires cool down. If you watched a film in reverse, you'd notice immediately. Things would look wrong, coffee would unpour into cups, splinters would reassemble into wood. These violations feel unnatural because they violate the entropy arrow. But here's the strange part. The fundamental equations of physics don't have an entropy arrow. Run them in reverse, and they work just as well. The one-way direction of time you experience emerges from the statistics of large systems, not from a fundamental law of physics that prefers one direction. The direction of time is an emergent property of the universe having started in an unusually ordered state at the Big Bang. Remove the low entropy beginning, and the arrow of time dissolves. This is one of the most disorienting results in modern physics. The direction of time, the most obvious feature of your existence, the thing that separates memory from anticipation, isn't written into the fundamental laws. It came from a statistical accident at the beginning of everything. Temperature emerged from particles. Time's arrow emerged from entropy. And some physicists believe time itself, the sequence, the duration, even the sense of becoming, emerges from correlations in a static quantum structure, the way temperature emerges from collisions that never stop. That comparison is powerful, but it also carries a weight, because if time is emergent the same way temperature is, then asking what time fundamentally is becomes a different kind of question. It stops being a question about clocks. It becomes a question about information, about what it means to be a physical system inside the universe, encoding a record of the states you've passed through. And that is where the story takes a turn that physicists are still processing. Drop a wine glass on a tile floor. It shatters into 100 pieces. Now wait, watch the floor for as long as you want. Those pieces will never leap back up, fuse themselves together, and land perfectly in your hand. Never. Not once. Not in the lifetime of the universe. That's entropy in action. Entropy measures how many ways a system can be arranged. A whole wine glass can only be whole in one way. All the pieces together in the right shape. A shattered glass can be arranged in an almost infinite number of ways. This shard here, that fragment there, dust scattered in different patterns across the floor. Disorder has far more options than order. Because disorder has more options, systems tend to drift toward it. A shuffled deck of cards is almost certainly in one of billions of possible disordered arrangements. A perfectly ordered deck, sorted by suit and number, is one in those billions. If you shuffle randomly, you'll almost never hit the ordered state. The math overwhelmingly favors disorder. This is why the universe trends toward chaos rather than complexity. Stars burn out, galaxies spread, heat flows from hot to cold, not the reverse. Everything tends toward the state with the most possible arrangements. And this tendency is deeply connected to why time feels like it moves in one direction. Think about a documentary recording your life. Every event you remember moves from order toward disorder. In some sense, the birthday cake is whole, then cut, then eaten and gone. The car is new, then worn, then rusting. Your body builds complexity for decades, then gradually loses the ability to maintain it. Every scene shows entropy increasing. Now imagine playing your life backward. The rust would leave the car, the cake would reassemble. This immediately looks wrong, because entropy would be decreasing instead of increasing. Your brain flags it as unnatural the way it flags a violation of physical law, because in everyday life, entropy decreasing is vanishingly rare. Here's the deeper point. Your memory records the past because the past had lower entropy. Lower entropy means fewer possible arrangements, which means more structure, more information, more distinguishable patterns. A structured past leaves traces. A disordered future doesn't, because disorder blurs into the same statistical noise regardless of what led to it. Memory only works in the direction of increasing entropy. Your brain can only form records of states that came from a more ordered condition. That's why you remember yesterday and not tomorrow. It's not because the future doesn't exist. It's because the future doesn't leave the kind of structured traces your brain can read. The arrow of time you live inside is a one-way corridor built from entropy statistics. But physics has known for over a century that the fundamental equations themselves don't prefer that direction. A recording of two particles colliding looks just as valid run forward or backward. Gravity, electromagnetism, the strong nuclear force, all of them work the same in either direction at the fundamental level. The one-way street you live on is a large-scale statistical phenomenon, and what created it is the universe's beginning. The Big Bang started the universe in an extraordinarily ordered, low entropy state. Tiny, hot, dense, structured. From that beginning, entropy has been climbing. The whole history of the cosmos, every star formed, every life lived, every thought, is one long fall from order into disorder. That fall is time, but the fall started somewhere, and that starting point raises a question so strange that physicists still argue about it today. The Big Bang was the most ordered moment in the history of the universe. That sentence is easy to say and nearly impossible to picture. We tend to imagine the Big Bang as explosive chaos, an unimaginably violent burst of energy, heat, and force. It seems like the most disordered thing possible. How could that be the most ordered moment? The answer requires thinking about entropy at cosmic scales. Order, in the physicist's sense, doesn't mean neat or calm. It means constrained. It means a system is in one of very few possible arrangements, rather than one of very many. When all the mass and energy of the universe was compressed into an incredibly small, dense, hot point, it was constrained to that one configuration. Almost no other arrangements were available. The system had very few possible states. As the universe expanded and cooled, matter spread out. Gravity pulled it into clumps, stars formed, planets formed, life formed. All of these structures look like order in the everyday sense. But in the thermodynamic sense, the available number of arrangements kept growing enormously. A universe with trillions of possible star positions and galaxy configurations has vastly more entropy than a universe crammed into a single point. Even if the spread out universe looks organized to human eyes, the universe started highly constrained. It has been relaxing into increasingly unconstrained arrangements ever since. That relaxation is entropy increasing. That increase is the arrow of time. Now here's what this has to do with your memory. Your brain forms memories by creating physical structures, connections between neurons that encode past states. Those structures work because the past had lower entropy than the present. A lower entropy past leaves cleaner, more distinguishable marks. Your neurons can build a reliable record of it because the structure of events was more constrained, more traceable. The future has higher entropy. Higher entropy means more possible arrangements. More possible arrangements mean less distinguishable structure. There's no clean pattern to record because the future hasn't yet collapsed into a specific path. From inside the universe, the past is carved into matter in readable traces. The future is a statistical fog. This is why you can recall your last birthday but not your next one. Physics, not just psychology. But here's where it turns genuinely disturbing. If the arrow of time depends on the universe starting in a low entropy state, then time's direction depends on initial conditions, on a fact about how things happen to be set up at the beginning. It's not a fundamental law, it's a consequence of a particular starting configuration. Change the starting conditions, and the arrow could reverse or disappear entirely. Some physicists have proposed that at some distant point in the future, if the universe reaches maximum entropy, time's directionality could become meaningless. Events would still happen, but past and future would be statistically indistinguishable. Memory would be impossible. No experience of temporal sequence could form. Others have suggested that the Big Bang's low entropy condition is itself crying out for an explanation. Why did the universe start so ordered? Calculating the probability of that starting configuration in a random quantum process gives a number so small it makes winning every lottery on Earth simultaneously look like a sure bet. The ordered beginning isn't just strange, it's statistically almost impossible. And the fact that time, your most intimate experience, depends on this near miracle at the dawn of everything, is a thought that doesn't get easier the longer you sit with it. There's something even more extreme waiting ahead. Imagine a sculpture the size of the universe. Every moment in history is frozen inside it. The Big Bang is there, at one end. Every star that ever burned, every life that ever lived, every thought that was ever thought, all of it carved into the structure in exact detail. And at the other end, every moment in the future that will ever exist, also there, also frozen, waiting in the sculpture, even though you haven't reached it yet. This is called the block universe. It isn't a fringe idea or a philosophical fantasy. It's a logical consequence of special relativity that physicists have taken seriously since Einstein's time. and it remains one of the most discussed interpretations of what space-time geometry actually means. Here's the argument for it. Einstein showed that there is no universal now. Different observers moving at different speeds disagree about which events happen at the same moment. What one observer calls right now happening simultaneously with this, another observer calls that happened a minute ago. Both are right. There is no privileged reference frame that settles the dispute. If there's no universal now, then there's no universal present sweeping across the universe like a wave. The concept of the present is an observer-specific label, not a global fact. But if the present is just a label, then so are the past and the future. They're just different parts of the space-time structure, like different countries on a globe. None of them is inherently more real than the others. They all exist. The past still exists in the geometry of space-time, the way a city you left yesterday still exists even though you're not in it anymore. The future already exists, locked into the structure of space-time, the way a city you haven't visited yet still exists somewhere ahead of you. All moments, past, present, and future, are equally real parts of the four-dimensional block. The moving present you experience is like the feeling of reading a book. The earlier pages don't stop existing when you turn to the next one. The later pages already exist even before you reach them. Your consciousness moves through the fixed structure of the story, generating the experience of sequence. But the story itself doesn't change as you read it. On the block universe picture, you don't move through time. Your consciousness moves through a fixed four-dimensional structure that already contains your entire life from birth to death. Every version of you at every age is already there, all equally real, all frozen in the sculpture. The sense that you are in the present, that the past is gone and the future hasn't arrived, is a feature of your limited perspective from inside the structure. From outside, if outside means anything, all the moments are just there. This idea is disturbing in a specific way that goes beyond ordinary physics puzzles. It means free will in the intuitive sense of genuinely creating the future as you go becomes extremely difficult to defend. If the future is already in the sculpture, your decisions tomorrow are already carved there. Your sense of choosing is the experience of moving through a structure that already contains the choice you'll make. Most physicists who take the block universe seriously don't claim it solves questions about free will. They point out that the sculpture could contain a version of you making free choices, and the experience of making those choices would be real even if the outcome was fixed in the geometry. But the shiver it produces is real too. The block universe doesn't make the flow of time feel less vivid. It makes the vividness strange. That sense of moving, of becoming, of being right here in the present has to be explained by something. Something has to generate the feeling of the present being special. And the most direct candidate is something that lives inside you. Right now, you feel present. You feel like you're here, in this moment, at a specific point in time. Not yesterday, not tomorrow. Now, that feeling is one of the most basic features of being alive. It shapes everything. Your sense of urgency, your experience of joy or fear, your feeling of existing as a continuous being with a past behind you, and a future ahead. But what if that feeling is built by your brain using nothing but memory? Here's the argument. Your brain doesn't have a sensor for time the way your eyes have sensors for light. There's no time receptor that detects the present moment and broadcasts it to your consciousness. The brain has no organ that directly experiences the flow of time. What it has is memory. Memory creates a record of past states. When you experience the present, your brain simultaneously compares it to recent records stored in short-term memory. The difference between what just happened and what's happening now generates the sense of time moving. The present feels present because it's different from what your memory recorded a moment ago. In a timeless block universe, this means something profound. You don't need time to flow for you to feel like it's flowing. You just need your brain to carry a record of past states and to compare that record to current sensory input. A creature with no memory would have no experience of time passing. It would exist in a kind of eternal present, not because time stopped, but because the mechanism that generates the sense of movement requires comparison between states. And without memory, no comparison is possible. This isn't speculation. It matches what happens to real people with severe memory disorders. Patients who cannot form new long-term memories often describe their experience as a kind of suspended present. They don't experience the accumulation of time. They feel trapped in a single, extended now because the mechanism that tracks temporal sequence has been damaged. This tells you something about where the moving now lives. It lives in the structure of your memory, not in the fabric of the universe. Now, extend this to the Wheeler-DeWitt picture. The universe's wave function is frozen. All configurations exist simultaneously in the mathematical structure, but physical systems inside the universe can carry correlations that act exactly like memory. A brain at time t has encoded within it a record of states that correspond to earlier configurations. When you look at any slice of the wave function containing a brain, that brain carries within its physical structure an imprint of what earlier slices looked like. The feeling of time moving is that imprint being read. The present moment feels real and vivid because your brain is a physical record-keeping system, and the act of record-keeping generates the sensation of being located in time. Some philosophers call this the memory theory of temporal experience. The idea has been around for decades, but takes on new weight in the context of a fundamentally timeless physics. The universe might be a static structure, the sense that you are surfing through it, moving from moment to moment, arriving at the present with the past behind you, might be the experience of being a physical system that stores information about its own states. Time feels like a river. It might actually be a library. And if the present moment is constructed from memory, then the question of what's actually out there, what the universe looks like stripped of all observers and their record-keeping systems, takes a sharp and unexpected turn. Cause and effect is the skeleton of reality. You flip a switch, the light comes on, the switch caused the light. The cause came before the effect. Every plan you make, every prediction you rely on, every piece of science ever done depends on this chain holding together. Causes precede effects. Effects don't reach backward and alter their own causes. But if time is emergent, that chain becomes something that needs explaining. In normal physics, causality is assumed. The equations describe how the state of the universe at one moment determines the state at the next. The arrow from cause to effect is built into the structure of time. Earlier moments drive later moments forward. Emergent time breaks this picture. If time is a pattern that appears inside a fundamentally static structure, then the sequence of cause and effect is also a pattern, not a fundamental law. Causality becomes something that emerges at the level of large, complex, memory-bearing systems, the same way temperature emerges from atoms that individually have no temperature. At the level of the wave function of the universe, there is no before, there is no after, there is only the full static structure with its internal correlations. The entire chain of causes and effects exists simultaneously in the mathematical object, the way the whole plot of a book exists simultaneously on every page. This is manageable if you accept the emergent picture calmly. Temperature is emergent but still real. Causality could be emergent and still real at the level where it operates. Your daily life would feel identical. But at the edges of physics, the loss of fundamental causality creates real technical nightmares. Black holes are one example. Inside a black hole, the geometry of space-time bends so severely that the concepts of before and after scramble. The singularity at the center isn't a place in space you can avoid. It's a moment in your future that you inevitably hit once you pass the event horizon. Space and time swap roles, as mentioned earlier, and the causal structure becomes so distorted that physicists can't agree on what it means for information to escape, be destroyed, or be preserved. This is related to the black hole information paradox, one of the deepest unsolved problems in physics. If you throw information into a black hole, does it survive in some form when the black hole eventually evaporates? The answer depends critically on whether causality and temporal order hold up at the quantum level near the singularity. And if time is emergent, there's no guarantee they do. The origin of the universe creates a similar headache. If time emerged from the Big Bang rather than preceding it, then the Big Bang itself has no cause in the ordinary sense. A cause requires a before. If time started at or near the Big Bang, there is no before. The question, what caused the Big Bang, may be as meaningless as the question, what is north of the North Pole? Some physicists find this liberating. The universe simply exists, with no external cause required, because the concept of cause requires time, and time is a feature of the universe rather than its container. Others find it profoundly unsatisfying. The whole structure of scientific explanation, the chain of why and how, runs on causality. A physics where causality is emergent rather than fundamental feels like a physics that has pulled its own foundations out from under itself. And what came next in this story pulled even harder. A 2025 paper described a universe so stripped down that the full mathematical description of everything that exists would fit inside a single point. The implications took the problem of time somewhere nobody had expected to go. In 2025, 3 physicists published a paper that made the rest of the field stop and reread it twice. Daniel Harlow, Mikhailo Yusatyuk, and Ying Zhao were working on one of the hardest problems in theoretical physics. How does quantum mechanics apply to a universe that is closed, meaning a universe with no outside, no edge, no external observer standing beyond its boundary looking in? Their answer came out clean, and it was shocking. In quantum mechanics, every system is described by something called a Hilbert space. Think of a Hilbert space as a room full of possibilities. A simple system has a small room with a few options. A complex system has an enormous room with an almost infinite number of arrangements. The size of the Hilbert space tells you how much information a system can hold, how complex it can be, how many different states it can exist in. For a single electron, the Hilbert space is tiny. For a cup of coffee, much larger. For a galaxy, unimaginably vast. For the entire observable universe with its hundreds of billions of galaxies and every particle in all of them, the Hilbert space should be so enormous it dwarfs any number humans have ever used. Harlow, Yusatyuk, and Zhao found something different. For a closed universe, one with no external reference frame, no outside, no boundary conditions imposed from beyond, the full quantum gravity Hilbert space appears to be one-dimensional, one dimension, a single point of possibility. In mathematical terms, a one-dimensional Hilbert space contains exactly one state. The universe, at its most fundamental quantum gravitational description, has only one configuration. There is nothing to distinguish. There is no complexity, there is no room for arrangement or rearrangement, just a single irreducible mathematical point. Sit with that for a moment. Every star you've ever seen in the night sky, every particle in your body, every memory you've formed, every thought you're having right now, in this framework, the universe containing all of that has a quantum description with the complexity of a single point on a line. This result comes from a fundamental feature of quantum gravity in a closed universe. When you have no external observer, no outside clock, no reference frame beyond the system itself, the constraints of general relativity and quantum mechanics together crush the available states down to one. The full universe, when treated as a completely self-contained quantum system, looks maximally simple. The paper immediately triggered a reaction across the field. Some physicists found it mathematically compelling, but conceptually catastrophic. If the universe is one state, where does all the richness of experience come from? Where do the galaxies go? Where do you go? Harlow, Yusatyuk, and Zhao had a proposed answer. You reconstruct it. Specifically, an observer inside the universe. A physical system with its own internal states, its own memories, its own degrees of freedom, can build an approximate description of experienced reality that looks rich and complex. The observer doesn't have access to the single global state. The observer has access to their own local corner of the universe. And from that limited corner, the universe looks like everything you know it to be. The full system is one point. The observer's view of that system is an entire world. And that gap between the simple truth and the rich experience is where time lives. The question now was, if observers have to reconstruct their experienced reality from inside a universe this simple, what exactly are they reconstructing? And what does that reconstruction have to do with the clock ticking in every second of your life? One is a strange number for a universe. When physicists talk about the size of a Hilbert space, they usually deal in numbers so large they require scientific notation just to write them down. The number of quantum states available to the particles in a room is something like 10 raised to the power of 10 raised to the power of 30. Stacking those exponents doesn't help you picture it. The number is beyond imagination. A Hilbert space of dimension 1 means exactly one state. To understand why that's so extreme, think about a coin. A coin has two sides. If you describe the coin quantum mechanically, it has a two-dimensional Hilbert space, heads, tails, or any combination of the two. The number 2 is already richer than 1. 2 gives you a choice. 1 does not. A one-dimensional Hilbert space has no choices. There is one state. The system is always in that state. There is no other arrangement it can be found in. There is no change, no evolution, no possibility of difference. And yet the universe contains all the difference in the world. How does a single state system produce the staggering variety of everything that exists? The answer requires understanding what a global description means versus a local one. The one-dimensional result applies to the full quantum gravity description of a closed universe, treated from no observer's perspective, from outside everything, from a completely detached mathematical vantage point that doesn't actually exist inside the universe. That vantage point, the view from nowhere, sees one featureless state. But observers don't live at the view from nowhere. You live inside the universe, embedded in it, surrounded by it, made of it. You only have access to a tiny fraction of its total information. Your senses reach a few feet, your instruments reach a few billion light years. Beyond that, you have no data. A physical observer inside the universe experiences something very different from what the view from nowhere sees. The observer has local degrees of freedom, meaning physical states and properties that belong specifically to their region, their body, their measuring instruments. Those local degrees of freedom can encode an enormous amount of information about the local corner of the universe. Harlow, Asatyuk, and Zhao propose that the observer's experienced reality can be approximately described by a Hilbert space whose size is determined by the observer's own entropy, meaning the number of physical arrangements available to the observer's own system. A human brain has a very large number of physical arrangements. A galaxy's worth of particles has an even larger number. The observer's local Hilbert space can be enormous even when the global one is one-dimensional. This is a radical restructuring of how physics usually works. Normally, you start with the universe, put observers inside it, and describe what they see. The universe is primary. Observers are secondary. In this framework, that order flips. The global universe is maximally simple. Observers are the source of perceived complexity. Reality as you experience it doesn't exist globally. It exists locally, from the inside, built up from the observer's own physical states, interacting with an environment that also has no absolute complexity at the fundamental level. The richness of experience is real, but it belongs to the observer, not to the universe itself. And when you ask what this means for time, the answer gets stranger still, because if complexity belongs to observers, then so does the clock. Picture the world's most detailed painting, millions of brushstrokes, thousands of colors, faces, landscapes, architecture, emotion, light and shadow layered over each other in extraordinary detail. Now imagine that from a great enough distance, the painting looks like a single, flat grey square. You can't see the faces. You can't see the brushstrokes. Everything collapses into a single, undifferentiated tone. The detail is real. The painting genuinely has all those brushstrokes. But the view from far enough away can't access any of it. This comparison captures something essential about the one-dimensional universe problem. The global quantum state of a closed universe is like the view from so far away that everything has collapsed into a single grey square. All the detail exists in the structure, in the correlations between the parts, but the view from outside the universe, the global perspective, cannot access that detail because the constraints of quantum gravity in a closed system reduce it to one state. The observer inside the painting, one of the faces in the portrait, sees everything differently. They see brushstrokes nearby, textures, shadows, neighboring faces. They experience the richness of the painting because they are embedded in it at a scale where the detail is accessible. The same logic applies to observers inside the universe. An observer is a physical system. They have internal states, brain configurations, memories, the positions of atoms in their body. Those internal states interact with nearby matter, absorbing information, recording it, building up a picture of the local environment. That process of interaction and recording is what creates experienced reality. The experienced world isn't something the observer discovers by looking out at an objectively complex universe. It's something the observer constructs through the process of interaction, using local correlations that the global description can't see. This connects directly to the relational time idea from earlier. Time in this picture isn't something the universe has. Time is something observers build by using one part of a local environment as a clock and tracking changes in everything else relative to that clock. The observer's internal states are the record. The changes in that record are time. A universe with no observers has no time in any meaningful sense. The static wave function sits there, the one global state exists, but no duration accumulates, no sequence forms, no before and after takes shape because no physical system is present to build those relationships. Add an observer, a physical system complex enough to encode information about its own states, and time emerges from the act of encoding. This isn't mystical, it's mechanical. The observer's physical states interact with the environment. Those interactions produce correlations. The correlations produce apparent change. Apparent change produces the experience of temporal sequence. The observer doesn't inject time into a timeless universe. The observer's physical complexity creates the structure that time is made of. This picture has been described as observer-centered reconstruction, building experienced reality from the inside out, rather than placing observers inside a pre-existing objectively complex universe. It matches the mathematics of the 2025 paper remarkably well. It also raises a question that is harder to dismiss than any of the ones before it. If time is rebuilt by observers, and observers are physical systems made of matter, then at some point in the very early universe, before any complex matter existed, before any observer of any kind was possible, what was time? Was it there at all? Here is the most unsettling version of everything covered so far. You are not inside time. Time is inside you. Specifically, time as a structured, directional, experienceable phenomenon may exist because your physical body is a record-keeping system sophisticated enough to produce it. Strip away the observer, strip away the memory, and the local correlations, and the embedded complexity, and what remains at the deepest level may have no time in it at all. This is disturbing for a reason that goes beyond abstract physics. It means the most fundamental fact of your existence, the sense that you are here, now, moving forward through moments, is a construction. Your brain assembles it from physical processes. The raw material is correlation and entropy, and the decay of ordered states. The experience is vivid, continuous, and utterly convincing, but it's assembled. The parallel most physicists reach for is color. The physical world has electromagnetic waves of different frequencies. Your visual system translates those frequencies into the experience of red, blue, green, and yellow. The color isn't out there in the wave itself. The color is the brain's way of representing information about frequency differences. Time may work the same way. Physical correlations exist, changes in entropy exist, causal relationships exist, at least approximately. Your brain translates those physical facts into the experience of past, present, and future, into the vivid sensation of moments arriving, passing, and being remembered. The translation is so seamless that the constructed experience feels identical to a direct readout of reality. But it isn't. There's a specific version of this that comes from the observer reconstruction idea. If your experienced reality is built from your local degrees of freedom, interacting with a universe that is globally a single quantum state, then your timeline is your local bookkeeping. Your past is a record stored in your physical states. Your future is the set of future states those physical processes are heading toward. The universe doesn't have a timeline. You do. And your timeline is as local and personal as your body temperature. This seems to suggest that different observers could have genuinely incompatible timelines. Not just timelines that measure slightly different durations the way Einstein showed, but timelines that disagree about sequence, about what came before what. At a more fundamental level, at large scales, this doesn't matter much. The physics of everyday life, of planets and people and chemical reactions, happens in a regime where observer timelines align well enough to produce a shared consensus reality. The emergence is robust, the approximation is excellent, but in extreme conditions, near black hole singularities, at the very beginning of the universe, or at the quantum gravity scale where the one-dimensional Hilbert space result lives, those timelines may diverge in ways that have no resolution. There may be no fact of the matter about what happened first, not because the measurement is imprecise, but because the very structure that makes sequence meaningful is observer-dependent. The philosopher in you might find this liberating. The physicist in you finds it a technical nightmare. Every calculation in cosmology assumes that space and time provide a shared background arena. Strip that background away, and the tools of the trade stop working at the scales where the real questions live. Physicists know this problem is there. They are working on it. A few lines of inquiry are showing genuine promise, including one that connects time to the structure of information storage at the deepest level of reality. That line of inquiry leads somewhere that sounds like science fiction but is grounded in serious mathematics. It leads to the idea that reality itself might be a kind of projection. Imagine your entire life stored on a piece of paper. Every memory, every physical sensation, every object you've ever touched, the depth of every room you've ever stood in, all of it encoded as information in a flat two-dimensional sheet. The paper doesn't have depth, but the information on it, read the right way, produces the experience of depth. This is roughly what holography means in physics. And it isn't a metaphor, it is one of the best supported ideas in modern theoretical physics, with roots in string theory and quantum gravity research that stretches back to the 1990s. The core idea came from work on black holes. Stephen Hawking showed that black holes have a temperature and slowly emit radiation, meaning they eventually evaporate. But where does the information about everything that fell into the black hole go? Physics demands that information can never be truly destroyed. The answer that emerged over decades of work was startling. The information isn't stored in the interior of the black hole. It's stored on the surface. On the two-dimensional boundary, the event horizon, every piece of information about every particle that ever fell in is encoded in the structure of that flat surface, the way a hologram encodes a three-dimensional image in a flat piece of film. This black hole result suggested something much larger. If the information content of a three-dimensional region of space is fully captured by its two-dimensional boundary, then maybe the universe itself works this way. Maybe the three-dimensional world you move through is the decoded readout of a two-dimensional information structure. This became known as the holographic principle. In its most developed mathematical form, called the anti-de Sitter/conformal field theory correspondence, or simply the duality, a complete quantum gravity theory in a volume of space is exactly equivalent to a quantum field theory living on the boundary of that space, one dimension lower, with no gravity at all. The mathematics of this equivalence has been tested and confirmed in thousands of calculations over 3 decades. It works. Now, here is where time enters again. In the holographic picture, the three-dimensional interior of the universe, including its time dimension, is an emergent description derived from the two-dimensional boundary theory. Time in the bulk, meaning time as you experience it moving through three-dimensional space, isn't present in the boundary theory in the same form. It emerges from the structure of the boundary's quantum states. Some researchers have gone further, arguing that not just time, but space itself emerges from quantum entanglement between parts of the boundary system. Two regions of space that are close together in the bulk correspond to parts of the boundary that are highly entangled. Space is woven from entanglement. Time is woven from the dynamics of that entanglement. This means the familiar dimensions you move through every day, length, width, depth, and time might all be emergent properties of a deeper quantum information structure that has none of those dimensions as fundamental ingredients. You don't live in space and time, you live in the decoded readout of a quantum information network. That idea is so far from everyday intuition that it seems untestable. But the holographic correspondence is mathematically exact, and calculations using it have produced physical predictions confirmed in labs studying systems like superconductors and quark-gluon plasmas. The holographic hint is real, and it connects directly to what quantum experiments are beginning to find about time's own twin. Two particles can be connected across any distance. Measure one, and you instantly know something about the other, regardless of whether they are across a lab or across a galaxy. This is quantum entanglement, and it has been confirmed in experiments so precisely that the measurements leave no room for doubt. The connection is real. It operates beyond the speed of light as a correlation, though it can't be used to send a signal faster than light. Einstein hated this result. He called it spooky action at a distance and spent years trying to prove it was wrong. He wasn't wrong. The universe really does work this way. But in recent decades, physicists have realized that entanglement might be more than a strange quirk of particle physics. It might be the building material from which space and time are made. Here's the argument. In the holographic picture, the three-dimensional interior of the universe corresponds to a two-dimensional boundary theory. The key bridge between the two is entanglement. Researchers found that the amount of entanglement between two regions of the boundary directly determines how connected the corresponding regions in the interior are. If you reduce entanglement between two parts of the boundary, the corresponding parts of the interior space pull apart. Reduce the entanglement all the way to zero, and the spatial connection between those regions disappears completely. Space tears. This means spatial distance, the fact that things are close together or far apart, is a measure of how entangled the underlying quantum states are. Space is the geometric expression of entanglement structure, and time in this picture emerges from the dynamics of entanglement. As quantum states on the boundary evolve and correlations shift, the interior geometry changes. What you experience as the passage of time, as moments flowing from past to future, is the interior's readout of how entanglement patterns are evolving on the boundary. The birth of time then might correspond to the moment when entanglement between quantum states first became structured enough to produce a coherent interior geometry. Before that structure existed, before entanglement organized itself into the pattern that generates a consistent space-time, there was no inside. There was no space for things to be in. There was no sequence for events to follow. Time wasn't born in an explosion. Time was born when quantum correlations first assembled themselves into the pattern that makes interior geometry possible. This is one of the most active research areas in theoretical physics right now, sitting at the intersection of quantum information theory, string theory, and general relativity. It goes by several names: emergent space-time, holographic space, or sometimes just quantum geometry. The experimental evidence comes mostly indirectly. The holographic duality has been used to calculate properties of strongly interacting systems in condensed matter physics, and the predictions match. Labs haven't built a device that creates space-time from entanglement, but the mathematics connecting entanglement to geometry has been tested in thousands of controlled calculations and holds up consistently. The implication for the time problem is stark. If time and space both emerge from quantum entanglement structures, then the Wheeler-DeWitt equation's timelessness isn't a flaw, it's a feature. It's describing the system at the level where entanglement lives, where there are no spatial or temporal dimensions yet, where the ingredients of geometry exist without the geometry having formed. Time doesn't disappear from the deepest equations because we wrote the equations wrong. Time disappears because time hasn't been born yet at that level. And in 2025, an experiment showed something that suggested time might not just be born once. It might come in two flavors. For your entire life, time has moved in one direction: forward. Always forward. Coffee cools down. It doesn't heat back up. Candles burn. They don't unburn every process you've ever observed has followed that one-way arrow. In February of 2025, physicists studying quantum systems published something that complicated that picture in a fundamental way. Researchers examining the quantum realm found evidence of two arrows of time emerging simultaneously from quantum processes. One arrow pointed forward, the standard one you're used to, the other pointed in the opposite direction. This wasn't a reversal of time as you experience it. Nothing in your daily life will suddenly start running backward. But at the quantum scale, the level of individual particles and their interactions, the rules of the game appear to allow both directions under specific conditions. Here's the clearest way to picture it. In ordinary physics, entropy always increases in one direction. Disorder grows as you move forward in time and decreases as you look backward. This produces one arrow, but quantum systems have a different kind of entropy, related not to the disorder of particles, but to the disorder of information itself, to how much you can know about a system, given what you can measure. When physicists examined quantum processes closely, they found that the quantum informational entropy can increase in both temporal directions simultaneously. Moving forward from some starting point, information disorder grows. Moving backward from that same point, information disorder also grows. Two slopes rising away from the same valley, one pointing forward and one pointing back. This means the quantum origin of time's arrow is not as simple as one direction imposed by disorder. It's richer. The quantum realm can produce temporal structure that runs in both directions from a single point. The immediate implication connects directly to cosmology. Some physicists have proposed that the Big Bang sits at exactly such a valley. Entropy was minimal at the Big Bang, meaning maximum order by the physicist's definition. From that point, the universe has been sliding down both slopes simultaneously. Our universe, the one you're in, moves in one direction as entropy climbs. A mirror universe, theoretically emerging from the same event, moves in the other direction, with its version of entropy also climbing away from the low point. That mirror universe would experience time running in the opposite direction relative to ours. From our perspective, it would look like time moving backward. From its own internal perspective, it would experience everything moving forward the same way you do, because time's arrow inside that universe also points toward increasing entropy from its own origin point. This is not an established fact about the universe. It is a theoretical picture that the 2025 quantum experiments made newly credible by demonstrating that two arrows can emerge simultaneously from a single quantum system. The deeper consequence is this: the direction of time may not be a fixed feature of reality. It may be a local property of which slope you're on. Different regions of the universe, or entirely different universes emerging from the same quantum event, could run in opposite temporal directions, each one experiencing itself as moving forward. The arrow of time that has felt like the most absolute fact of your existence turns out to be a local address. You're on one slope, someone else might be on the other. And if the direction of time can vary, the question of whether time itself can be completely absent in some contexts becomes harder to avoid. The Big Bang produced one universe. Most people assume that's the full picture. One explosion, one expanding cosmos, one arrow of time pointing forward from that beginning. Some physicists think the picture has a reflection. The mirror universe idea, sometimes called the CPT mirror universe or the two-sided cosmology, proposes that the same quantum event that produced our universe also produced a second one, extending in the opposite temporal direction. Where our universe runs forward from the Big Bang, its mirror runs backward, or equivalently from the perspective of beings living in it, forward in the other direction. The idea rests on a deep symmetry in physics called CPT symmetry. C stands for charge, meaning positive and negative. P stands for parity, meaning left and right. T stands for time, meaning forward and backward. The combined CPT operation flipping all three simultaneously is one of the most fundamental symmetries in all of particle physics. Experiments have tested it to extraordinary precision. The laws of nature appear to respect it exactly. What that means is this: If you built a universe where all particles were replaced by their antiparticles, all spatial coordinates were reflected as in a mirror, and the direction of time was reversed, the laws of physics would operate identically. Nothing in the fundamental rules would be different. A mirror universe with time running the other way is physically legal. In the two-sided picture, the Big Bang sits at a junction point between two universes. Our universe extends in one direction from that point, growing, cooling, and running forward in the direction we call the future. The mirror universe extends in the other direction, also growing and cooling from its own perspective, its own version of forward being what we would call the past. Neither universe knows the other exists. Observers in our universe have no way to see across the junction. The junction point, the Big Bang, is the edge of accessible time for us. The mirror universe lives on the other side of an edge we can never cross. The matter in the mirror universe would be antimatter from our perspective. That matters because one of the long-standing puzzles of cosmology is why our universe seems to have so much more matter than antimatter. A symmetric creation event producing a matter universe and an antimatter mirror universe would solve that puzzle elegantly. The total matter and antimatter in the combined system would balance perfectly. We're sitting on the matter side. This idea is consistent with the CPT symmetry that physics absolutely requires. It makes no prediction that has been directly tested because the mirror universe is inaccessible by definition. It remains a theoretical framework, a serious one developed by physicists, including Neil Turok and Latham Boyle, but not yet confirmed. What it adds to the time problem is significant. If time's direction is determined by which side of the Big Bang you're on, then the arrow of time is not a universal feature of physics. It's a boundary condition. An observer at the junction point, if such a perspective were possible, would see time running in both directions simultaneously, with no preferred arrow. From that vantage point, the universe would look genuinely timeless. Not because time doesn't exist, but because both directions exist equally and neither is more real than the other. The problem of time isn't just about whether time is fundamental. It's about whether the direction that makes time feel like time is anything more than the accident of which side of a symmetric event you happen to land on. Every serious physicist who looks at Gödel's time loops reaches the same conclusion. They probably can't happen. Something probably prevents them. The word probably is doing a lot of work in those sentences. What physicists mean is this: no experiment has ever shown a closed time loop. No traveler has ever arrived before they departed. No effect has ever been observed arriving before its cause. The track record of the universe suggests strongly that whatever Gödel's equations permit, the universe has found a way to prevent it. But physics has never pinned down the mechanism. Stephen Hawking's chronology protection conjecture, proposed in 1992, was the most direct attempt. Hawking argued that whenever conditions arise that could produce a closed time loop, quantum effects amplify without limit at the moment the loop would form. Radiation and fluctuations pile up at the critical point and either prevent the loop from completing or destroy the physical situation that would have created it. This is a beautiful idea. It uses quantum mechanics, the theory of the very small, to enforce a rule that classical general relativity fails to provide. But it's still a conjecture. Hawking himself acknowledged it was more of an educated expectation than a derived result. A full calculation would require a complete theory of quantum gravity, which doesn't exist yet. The conjecture sits in the scientific literature as a well-motivated guess that the universe probably agrees with but hasn't been formally proven. Other approaches have looked for causality protection in the structure of quantum information. If information is fundamentally conserved, and if closed time loops would create paradoxes where information is duplicated or destroyed, then perhaps the universe's protection of information automatically prevents the loops. This argument is attractive, but also incomplete. Some physicists have taken a different route entirely. Instead of looking for a mechanism that prevents time loops, they've suggested that time loops might be self-consistent in a way that avoids paradox. On this view, if a time traveler goes back to prevent something, the very act of going back was already part of the sequence of events that led to the attempt. Nothing gets changed. Everything that happens in the loop already happened, consistently, with no contradiction. This is called the Novikov self-consistency principle. It resolves the grandfather paradox by insisting that if you went back and tried to prevent your grandfather from having children, something would stop you. Not because of a law, but because that's what already happened. You already failed. The timeline is fixed. This principle is logically consistent, but it comes with its own strangeness. It means that in a universe with time loops, free will becomes difficult to define. Every action you take in the past was predetermined by the fact that the loop is consistent. You can try to change things, but you will always fail in exactly the way needed to preserve the loop. None of these approaches resolves the problem definitively. The universe appears to protect causality. Physics hasn't explained why. The most fundamental theory of space-time, general relativity, doesn't build in that protection. The most promising candidate for an explanation, quantum gravity, remains unfinished. This gap between what the equations allow and what the universe seems to enforce is one of the clearest signs that physics is missing a deeper principle. Something governs the relationship between time and causality at a level below general relativity and below quantum mechanics as currently understood. Finding that principle would change physics completely. It might also reveal why the universe chose to have time at all. The universe began about 13.8 billion years ago. That sentence sounds simple, but every word in it becomes complicated once you take seriously the idea that time is emergent. Start with began. To begin means to start existing at a certain time. But if time is emergent from the universe, then the universe can't have begun in time the way a conversation begins at a certain hour. The universe isn't a thing that happened inside time. Time is a thing that happened inside the universe, or rather, a thing that emerged from it. This is not just a linguistic puzzle. In standard cosmology, the Big Bang is treated as the earliest moment, the point from which time runs forward. The equations of general relativity run backward, lead to a state of infinite density and temperature at a finite time in the past. That's the singularity. That's where the model breaks down, where the equations stop giving finite answers and become meaningless. Physicists generally interpret this breakdown as a sign that general relativity isn't the right tool at that extreme scale. Quantum effects become crucial. A full quantum gravity theory is needed to describe what actually happened at or before the Big Bang. And in quantum cosmology, the Big Bang looks different. In the Wheeler-DeWitt framework, the wave function of the universe isn't something that was created at the Big Bang. It's a timeless object that contains all configurations of the universe, including the extremely compact early configurations and the spread out late ones. The Big Bang isn't a moment when the universe started. It's a region of the wave function's configuration space where matter was extremely dense. There was no before because the configuration space doesn't have a direction that corresponds to a temporal before. The wave function is static. All the configurations coexist in the mathematical structure. The sequence of events, the Big Bang, followed by expansion, followed by cooling, followed by galaxies, followed by you, is a path through the configuration space, not a journey through pre-existing time. Time emerges along that path. Before the path reaches the configurations corresponding to an early dense universe, there are configurations that correspond to even earlier or to something else entirely. But earlier here doesn't mean earlier in time. It means a different region of a timeless mathematical space. This is where asking what happened before the Big Bang becomes genuinely unanswerable. The question assumes that time exists before the configurations labeled early universe. In the emergent picture, time comes with those configurations. There's no time region to look into that precedes them. The analogy that keeps coming up among physicists is asking what is south of the South Pole. The question assumes that south continues past the southernmost point. It doesn't. South is defined by the structure of the globe, and the structure runs out at the pole. Time is defined by the structure of the wave function's correlations. And asking what came before those correlations emerged is asking about a region where the word before has no meaning. But this leaves a real puzzle. If time emerged, then there was a configuration, some state of the wave function, from which time had not yet emerged. Does anything distinguish that state from the state where time has emerged? What is the physics of the transition from timeless to temporal? This question has no accepted answer. What physicists are confident about is that the beginning of time, if that phrase means anything, is not the start of a clock that was already ticking. It's the appearance of the mechanism that makes clocks possible. And what created that mechanism connects to a possibility that no one expected. Here is the honest state of the question. Nobody knows. What physicists do know is that the Big Bang marks the limit of the current models. Run general relativity backward, and you hit a singularity, a point where the math breaks and stops producing physical answers. That boundary is real in the sense that it's where current tools fail. But two serious scientific frameworks suggest the Big Bang might not be the absolute beginning of time. The first is loop quantum cosmology. This is a version of quantum gravity that modifies general relativity at the smallest possible scales, replacing the singularity with a bounce. Before the Big Bang in this picture, there was a contracting universe. The contraction reached a minimum size set by quantum geometry effects, and then rebounded into the expansion we observe. The Big Bang is a bounce point, not a beginning. If loop quantum cosmology is correct, time extended through the bounce. Our Big Bang was a transition, the bottom of a cycle between a contracting past and an expanding future. The universe before the bounce would be inaccessible to us in practice. The quantum effects at the bounce would scramble any information about the pre-bounce era beyond recovery, but time itself continued through. The second framework is the no-boundary proposal, developed by Stephen Hawking and James Hartle. This is a different approach that treats the very early universe using a mathematical technique borrowed from quantum field theory, one that allows time to smoothly become a fourth spatial dimension near the beginning. In this picture, asking what happened before the Big Bang is like asking what's north of the North Pole. There is no north. There is no before. The early universe curves around so that the beginning has no edge, no prior moment, no boundary. In the Hartle-Hawking picture, time isn't something that was created at the Big Bang. It's something that emerged gradually from a regime where temporal and spatial directions were indistinguishable. The beginning of time was a smooth transition out of a state where the word time had no meaning, not a sharp starting edge. Both of these frameworks are scientifically serious. Both remain incomplete. Neither has been confirmed by observation, partly because the signatures of quantum gravity effects at the Big Bang, if they exist, are extremely difficult to detect in the cosmic microwave background or other observables. What's clear from both is that the Big Bang as the literal moment of time's creation may be an artifact of using the wrong tool, general relativity without quantum corrections, at the scale where it breaks down. The true origin of time, whatever it is, lives in a regime where quantum gravity is essential, and where the question itself may need to be reformulated before it can be answered. The most honest summary: the Big Bang is where time becomes meaningful for observers like us. Whether it is where time began in any absolute sense is a question current physics cannot answer. And that uncertainty, far from being a weakness, points to the place where the next revolution in understanding will happen. One of the most pointed ways to see why involves asking what the universe would look like to a being with no limits, no position, no perspective. Because the attempt to answer that question led directly to something physicists are still arguing about. If time is something observers build from inside a static universe, then the most intimate experience of your life is a construction. This chapter is about what that means for the experience itself. The experience of time is not a single thing. It has several layers. There's the sense of the present moment, the feeling of being here now. There's the experience of duration, the way 5 minutes feels short or long depending on what you're doing. There's the directional feel of past and future, the sense that you've come from somewhere and are heading somewhere. And there's the experience of becoming, the feeling that you are developing, changing, getting older. In the emergent picture, each of these layers has a physical explanation that doesn't require time to be fundamental. The sense of the present moment comes from the brain's continuous comparison of current sensory input with recent memory. The feeling of now is the experience of that comparison happening. The experience of duration comes from the amount of information processed during an interval. Dense, stimulating experiences feel shorter in retrospect because they pack many distinct states into a compact memory. Boring intervals feel longer because each moment is less differentiated from the last, making the stored record feel stretched. The directional sense of past and future comes from entropy. The past is carved into the physical structure of your brain as memory. The future is statistically open. The experience of becoming comes from the physical process of change itself: neurons firing, proteins folding, cells dividing. Each of those processes leaves a physical trace that distinguishes what was from what is. All of this is real, all of it happens. The construction doesn't make it less true, but here's where it becomes unsettling. Consciousness is the one place where the view from nowhere meets the view from inside in a way that physics hasn't resolved. You experience time. That experience is a real physical process in your brain. But the fact that there is something it is like to be you, that these physical processes produce a felt quality of time passing rather than just a mechanical readout, is one of the hardest problems in all of science. The hard problem of consciousness, the question of why physical processes produce subjective experience at all, is separate from, but deeply entangled with the problem of time. If time is emergent, then subjective temporal experience is doubly constructed. The sequence of events is a pattern in a static structure. The felt quality of moving through that sequence is something generated by the physics of your brain interacting with that pattern. What's genuinely unknown is whether the observer dependence of time in quantum cosmology has any connection to the observer dependence of consciousness. Some physicists and philosophers have suggested a deep link, that the reason the universe needs observers to generate time might be related to the reason that physical processes generate the experience of time. This is speculative. It is not settled science. Most physicists are cautious about connecting quantum cosmology to consciousness because the scales are so different and the concept so slippery. But the structural similarity is hard to ignore. In both cases, something that feels fundamental, time in physics, experience in consciousness, turns out to be built from simpler ingredients at a deeper level. In both cases, the building happens from the inside. And in both cases, the thing that emerges from the building process is more vivid and more certain than the ingredients it was built from. You are more sure of the present moment than you are of any physical theory. And yet, the present moment may be the most sophisticated trick in the universe. Physics has two great theories. General relativity describes the very large. Galaxies, black holes, the expansion of space. It is spectacularly accurate. The predictions it makes about gravitational waves, black hole shadows, and the bending of light around massive objects have all been confirmed to precision that should make you dizzy. Quantum mechanics describes the very small, atoms, particles, the behavior of energy at tiny scales. It is also spectacularly accurate. The predictions it makes about the behavior of electrons and photons have been tested and confirmed to more decimal places than any other scientific theory in history. The two theories are individually the most precisely confirmed ideas humans have ever developed, and they are fundamentally incompatible. The incompatibility runs deeper than a technical mismatch. It's a philosophical collision. General relativity treats space-time as a smooth, continuous structure. The geometry of space and time can bend and flex, but it has a definite shape at every location. You can, in principle, point to a specific region of space-time and describe its curvature exactly. The theory is deterministic and geometric. Quantum mechanics treats everything as probabilistic and fuzzy at small enough scales. Position isn't definite until measured. Energy comes in chunks. The very act of observing something changes it. Uncertainty isn't a failure of measurement. It's a feature of reality. Apply quantum mechanics to space-time itself, and the problems pile up instantly. Space-time in quantum gravity would have to be fuzzy. Space would fluctuate, time would fluctuate. The geometry that general relativity uses as its foundation would be subject to quantum uncertainty at scales of around 10 to the negative 35 meters. The Planck length, a distance so small that comparing it to an atom is like comparing an atom to the entire observable universe. At that scale, the smooth space-time of general relativity dissolves into a quantum foam. Space-time geometry is no longer definite. It's a superposition of many possible geometries simultaneously. And time, which is part of space-time geometry, becomes part of the fog. Every serious candidate for a theory of quantum gravity runs into the problem of time immediately. String theory, the most developed candidate, is beautiful mathematically and contains versions of the holographic principle that have proven extraordinarily useful. But it hasn't produced a clean, definitive description of time at the Planck scale, and its core formulation still relies on a background space-time that a truly complete theory should derive rather than assume. Loop quantum gravity, the main competitor, quantizes space-time directly, treating space itself as a network of discrete quantum chunks. It avoids some of string theory's assumptions, but produces a Wheeler-DeWitt style equation with no external time, running directly into the problem of time. Causal set theory treats space-time as fundamentally discrete, a set of events with causal relationships between them. Time emerges from the partial ordering of those causal relationships. The approach is elegant, but difficult to connect to the observed continuous space-time of everyday experience. Every road leads back to the same intersection. Something has to be done about time. Either time is a fundamental ingredient that the theories need to include properly, or time is emergent and needs to be derived from something more basic. Either way, current theories haven't fully resolved the question. This is the center of the problem. The incompatibility between general relativity and quantum mechanics isn't primarily a technical puzzle about calculations. It's a puzzle about what time is. The two theories have different incompatible assumptions about the nature of time baked into their foundations. A theory of quantum gravity isn't just a bigger, better calculator. It requires a decision about time at the deepest level, and no one has agreed on which decision to make. This is the question that makes the whole problem personal. If the deepest description of the universe has no time, if the master equation is frozen, if the present moment is constructed by observers from correlations inside a static wave function, then what would it feel like to live in such a universe? The answer, and this is the part that should give you pause, is that it would feel exactly like this. It would feel like waking up every morning with a sense of time having passed overnight. It would feel like memories of yesterday, anticipation of tomorrow, urgency about deadlines, nostalgia for childhood. It would feel like minutes dragging during a dull class, and hours vanishing during something you love. It would feel like you are moving through time, surrounded by time, embedded in time, because you are. The emergent picture doesn't say time is fake. It says time isn't fundamental. Those are different claims. Temperature isn't fundamental. It emerges from the motion of atoms. But hot coffee is genuinely hot. You feel it genuinely burn if you grab it too fast. The emergent nature of temperature doesn't make it less real for the system that experiences it. Pain isn't fundamental. It emerges from nerve signals and brain processes. But pain genuinely hurts. The emergent nature of pain doesn't make the hurt less real for the person feeling it. Time isn't fundamental. It emerges from correlations, entropy, and the physics of memory-bearing observers inside a static wave function. But time genuinely passes. The seconds genuinely accumulate. The present genuinely feels present. The emergent nature of time doesn't make it less real for you. What it changes is the level at which the explanation lives. The reason time exists is deeper than time is a basic ingredient of the universe. The reason is something like the universe has a structure and physical systems complex enough to encode their own states extract temporal sequence from that structure. The richness of your temporal experience is a measure of how complex a system you are, not a direct readout of a fundamental feature of reality. This is, in one sense, humbling. You are not inside a pre-existing temporal framework, you are the framework. In another sense, it's extraordinary. You are the process by which a fundamentally timeless universe experiences itself as temporal. The universe at its deepest level has no clock, but through you, it does. There's a version of this idea that resonates far beyond physics. Every culture that has ever existed has had some intuition that time as experienced by humans is different from some deeper, eternal structure underlying reality. Philosophy, religion, and poetry have circled this idea for thousands of years. The physics lands in a very different place than any of those traditions, derived by completely different methods with very different precision. But the structural conclusion that the flow of time is something that emerges for observers rather than something that exists prior to observers echoes across the history of human thought in a way that is hard to dismiss as coincidence. The answer to what it would feel like to live in a timeless universe is like this. Exactly like this. Physics doesn't have one answer to the problem of time. It has three families of answers, each internally coherent, each supported by serious researchers, and none of them fully confirmed. Understanding why no single answer has won clarifies how deep the problem actually runs. The first family says time is real and fundamental, but is being described incorrectly by current theories. On this view, the Wheeler-DeWitt equation's timelessness is a sign that canonical quantum gravity is an incomplete formulation, not a sign that time is emergent. The goal is to rewrite the foundations so that time appears explicitly in the deepest equations. Some researchers in this family have developed what they call a Wheeler-DeWitt equation, with time adding an explicit time variable through a careful treatment of boundary conditions, or by modifying the quantization procedure. Others argue that a future theory of quantum gravity will restore a privileged notion of time at the fundamental level. The appeal of this approach is that it matches intuition and preserves the everyday structure of physics as closely as possible. Its challenge is that every attempt to reinsert time by hand looks arbitrary. No one has found a natural, principled reason to prefer one time variable over another, or to justify the reintroduction of time in a way that satisfies most of the field. The second family says time is emergent, and the goal is to explain how. The relational time approaches, the Page-Wouters mechanism, the entanglement-based space-time ideas, and the observer reconstruction framework from the 2025 closed universe paper all belong to this family. Time is real at the level of experience and large-scale physics. It is derived from deeper, timeless ingredients, correlations, entropy gradients, quantum information structure. The appeal of this approach is that it accepts the mathematics honestly. The equation has no time. Start there and derive time from what the equation does have. The challenge is that different choices of internal clock produce different quantum theories, and no one has found a unique, preferred way to make time emerge that everyone agrees on. The Cambridge 2025 result, showing that ordered succession, duration, and directionality can emerge from Wheeler-DeWitt cosmology, is a significant step forward, but it doesn't uniquely select one derivation over others. The third family says the problem is with the framework itself, and the solution requires ideas not yet fully developed. Holographic approaches, causal set theory, loop quantum gravity, and some versions of string theory all suggest that space and time are not the right starting point. The right starting point might be quantum information, causal relationships, or discrete combinatorial structures from which space-time emerges at large scales, the way fluid dynamics emerges from molecular motion. The appeal of this approach is its ambition. If space and time are both emergent, then the problem of time dissolves into the more general problem of deriving space-time from something deeper, and that problem might be tractable in the new framework. The challenge is that none of these frameworks is complete, testable in the regimes where they matter most, or agreed upon by the field. The reason no family has won is that the problem of time requires an experiment that can probe the Planck scale, the scale of around 10 to the negative 35 meters, where quantum gravity effects dominate. Every experiment ever performed sits far above that scale. The physics that would distinguish between these approaches happens in a regime completely inaccessible to current or near future technology. What physicists can do is test the mathematical consistency of each approach, check whether it reproduces known physics at large scales, and look for indirect signatures in cosmological data. None of those tests has delivered a decisive result. The problem of time is open, genuinely, seriously, foundationally open. Everything in this video has been building toward this moment. Right now, the present, you here, aware of being aware. Is it real? The answer depends on what real means. The sequence of chapters you just moved through is real. The discoveries are confirmed, the mathematics is solid, and the problems are unsolved but not invented. Physics genuinely doesn't know what time is at its most fundamental level. That's not a dramatic overstatement for the sake of a video. It is the honest current state of the science. But here is what follows from that honesty. If time is emergent, then the present moment isn't real in the way a fundamental particle is real. It doesn't exist as a basic ingredient written into the deepest laws. It exists the way temperature exists, the way music exists, the way the color red exists. Real, vivid, causally powerful, meaningful, and made of something else at a lower level. Your memory is real. The physical structure in your neurons that encodes yesterday is a genuine arrangement of matter that affects how you behave today. The correlations between that structure and the states of the world that produced it are real correlations. Your present moment is real. The convergence of sensory input, memory comparison, and neural processing happening right now is a real physical event. You are genuinely here. The future is real. It exists in the block universe structure, or equivalently, it is the set of configurations the wave functions correlations are pointing toward from your current position. Whether you experience it as open and free, or fixed and determined, is a question about free will that physics hasn't settled, but the configurations are there. What isn't real, in the sense of being fundamental, is the flow, the felt quality of time passing, of the present being special, of the future being genuinely different from the past in some metaphysical sense. That part is you. That part is the process of being a physical observer embedded in a universe that generates temporal structure through complexity and correlation. The present moment feels like the most real thing in the universe. It might be the most constructed. Both of those things are true at the same time. And sitting with the tension between them is one of the most honest intellectual positions you can occupy. Scientists are working at the edges of where current tools fail, in the quantum gravity regime, in the mathematics of observer reconstruction, in experiments probing the quantum origins of time's arrow. Some of the most talented humans alive are spending their careers on exactly this problem. They haven't solved it. That's not a failure. That's the frontier. The fact that the present moment, the thing you are most directly experiencing right now, is at the center of one of the deepest unsolved problems in all of physics, is something worth carrying with you. You are a physical system complex enough to generate the experience of time in a universe that may not have time built in. The universe runs through you in a specific sense. You are not a spectator watching time pass. You are part of the process that makes time real. If you've made it here and you want to keep exploring questions like this, liking and subscribing helps more than you might think. The next time you feel a second pass, remember what that second might actually be. Something extraordinary dressed up as something obvious.